All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108, the final edition of our course material. I decided to just re-record this because I can't bother dealing with combining the videos from last time. So we finished our review not long ago, so I decided that, hey, let's just do it right now. Since I'm already here, I'm already set up. Let's actually just jump into it. Okay, there we go. Okay, so again, just to reiterate, everything covered in this lecture is going to be bonus material. So you don't really have to know it for that lecture, except what is right here, the central tendency and average. This is going to be a recap of what we did in last class. So this you are responsible for, but what I'm going to do in the next section, which is covering variation, technically you don't need to know this for the final unless you want to get some extra points, which I think will be worth it because it's just a lot of formulas and plug and chug. If you know the formulas, it shouldn't be too bad. So last time, what we were doing is we looked at central tendency and average. We noticed that sometimes data has behavior that we want to notice. So for example, it will have a peak. And because statistics, the goal is to be able to answer questions about what typically happens, where the peak happens is something that we'd want to know. So this is going to be where a lot of data points come together. So what we'll do is we want to know where that is, right? So this is the value that the data points clump around to create this peak. It's called the central value. And this property that data has in clumping around certain values is called central tendency. And we came up with a measure called an average to approximate what this value is that our data points clump around. So that is what an average is. And there were several types we saw. There was the mean, mode, median. There are more, but these are the three important ones. So the mean is just the sum of all the values in a data set divided by the number of values in the data set. So there's another way to write that down, which I guess I can write here. So that is like if if x1, x2, x3, dot, 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 xn is the data set, then the mean is equal to x1 plus x2 plus x3 plus xn all over n. There's another way of writing this with this sigma sign. I mean, I think we've seen it before, where we say xi, where that I can go from 1 up to n, all over n. Right, so that's the formula for the mean. The mode is just the guy that shows up most frequently. The median is the middle value. So we saw that if we had an even number of values, the median is going to be the mean average of the two middle values, which is you add them together and divide by 2. If you have an odd number of data points, the mean, there's going to be a value exactly in the middle, and you just pick that. So we had a set of data here where we had to calculate the mean, the mode, the median. So for the mean, you just add all the data points divided by the number of data points there are, you got that. The mode was the guy that showed up most often. That was 12, showed up 3 times, more than any other person. The median, we first rewrite in ascending order. There were an even number of numbers, so we picked the 2 in the middle. We averaged them in terms of the mean average, and we found that. So it turns out for this, the typical values were found to be around 8 for the mean and the median, and for the mode would be 12. Although 8 is probably more trustworthy here. We have 2 guys agreeing versus the other. 12 doesn't show up that much more often for us to assume it's typical. But these are just some measures of what the typical value in a data set is. And those were those three. So that's what we looked at last time. Now we're going to move on to another topic called variation. So let's actually do that. So variation is another way to analyze data sets, because sometimes just knowing what the typical value isn't really enough to kind of talk about the data set in as much specificity as you would want. Okay, so variation is another measure that we can use to actually talk about data. And variation is just referring to how the data is spread out around the central value. This might be of importance also. And the numerical value that we assign to measure variation is called variance. We'll talk about a specific kind of variance later on, but that's the word we use. And we might think, well, why is variation important? Well, look at this example here. We have two data sets, 4, 10, 16, 22, 22, 28, 34, 40. We have another data set, 19, 20, 21, 22, 22, 23, 24, 25. Now, if you were to calculate the median, the mean, and the mode of these two data sets, you would get 22 for both of them, which means in terms of averages that we've looked at last time, these two data sets are indistinguishable. We can't tell the difference between the two, which is obviously a problem because there should be a clear difference between these two data sets, right? One ranges from like 4 to 40. That's a very wide gap. Whereas in the second data set, we're mostly in the 20s. There's like one value that's outside of the 20s, and it's very close to being 20s, in the 20s. So one data set is a lot tighter than the other one. It's not as spread out around the average, right? So we'd want to be able to know when this happens, right? So that is where variation comes in. The difference in these two data sets do not come from averages, they come from the spread. So how do we actually measure spread? Well, there are a couple ways. We'll go over about 3 of them. So one I just actually mentioned was the range, right? So the range is just the span of the data. It's kind of the difference between the smallest and largest values. In fact, it is exactly the difference between the smallest and largest values. So the range is given by this formula right here. Take the highest value, subtract the smallest value, and that gives you the range. It's the difference between the largest and smallest values, right? So for example, in the data sets above, we can now tell the difference. The smallest value in the top one was 4, the largest value was 40. So we're going to take 40 minus 4. In set 2, the largest value was 25, the smallest was 19. We're going to take 25 minus 19. And you will notice that now we have a difference between these two data sets that we can see. We can see that the first data set is spread out a lot more than the second data set. The first data set is spread out over a length of 36, while the second data set is spread over a length of 6. Okay, so that's one way. Now, it turns out that the range can also be an issue. For example, if you look at this example, 2 more data sets. So I have one data set, 20, 45, 66, 70, 75, 100. And the second data set, 20, 90, 95, 95, 98, 100. You will notice that the range for both of these is the same. It's 80. However, if, for example, these data sets were grades of students, it's clear that the second set of grades is better than the first. In the second set of grades, you have most students in the 90s, even a student getting 100. Whereas in the first data set, you have students getting 20s, 45, 60s, and in the 70s. You only have one student getting an A in the first data set. And that's something, again, you'd want to know. But here, the range wouldn't really help you to know that because you'd have the same range for both of these, right? So the range is 80 for both, right? So range also has its limits, just measuring the highest and lowest value. So we come up with other ways to measure variation or spread of data. Another way is the quartile, right? So using quartiles. Now, quartiles, from the root word quarter, right? It means you're going to split your data into 4 equal sections, where roughly 25% of the data is in each section. So the first point, right? So when you're splitting up data into 4 parts, let me do that. So you're splitting data into 4 parts, where you want roughly 25% in each part. Notice that you would need 3 points to split that into, right? So there's these 3 points, right? So those are the points you'd have to identify to know how to spread your, how to create these quarters, okay? Now those guys are called the quartiles. Now the first one is what we call Q1. The second one is what we call Q2. The third one is what we call Q3. Now, of course, you'll notice at Q2, there's 50% of the data on either side. That is specifically what the median does, right? So Q2 is going to be our median. Now, what you want to do for Q1 and Q3, it's going to be another median. But so Q1 is going to be the median of all values below the median of the entire data set. Q3 is going to be the median of all values above the median of the entire data set. This is going to split the data into 50%. And then split each half into 50%. So you'll get 25% each in each section, right? So this is another way that we can split up data, right? So we can have these quartiles. And that's pretty much their definition. We know how to find the median from last class. So we're okay. So now we can move forward. So for example, for set 1 of the data, the same data set we had above. So maybe I should copy that. 20, 45, 66. This was our data, 20, 45, 66, 70, 75, 100. Okay. So you want to find the median. We know that here, this is that's halfway. There's 3 on either side, which means the median is going to be the average of these two, the mean average. So Q2 equals the median. This is equal to, well, 66 plus 70 all over 2. It's going to be 68. So that's your Q2. Now, when you look at Q1 and Q3, Q1 is when you're looking over here. So Q1 is going to be the median. So Q1 equals median of this. So that's just 45. Q3 is going to be the median of all data above the actual median. So Q3 equals the median of these guys. So that's your 75. And so that leads us to that. And we can find these similarly. For set 2. Okay. So that's it. You just go through and you find medians, right? Median of the entire data set is Q2. Median of the guys below that is Q1. Median of guys above that is Q3. So you just find the medians 3 times, right? And these are the quartiles. This is how you're going to split the data, right? Now, analyzing quartiles, you can get 2 important notions out of this. One is the interquartile range. This is just the difference between Q3 and Q1. So you take Q3, subtract Q1, and that's the difference. So here, if you look at these 2 data sets here, Q3 minus Q1 for set 1, that would leave you with 30. Q3 minus Q1 for set 2, that would leave you with 8, right? So here you'd realize that interquartile, the ranges are different, right? So even though the entire range of the entire data set is the same for both, the interquartile range is different for both. So we already start seeing the difference between data sets here. Right. Now, the next thing that we can get here by analyzing quartiles is another kind of chart. Chart is called a box plot or a whisker plot because it's literally a box with like two whiskers coming off of it. So it's essentially a chart that plots the quartiles, and the interquartile range is represented by a box. You'll have a line slicing through this box representing the location of the median, and you will have two whiskers extended from either side. That goes all the way down to the lowest value and all the way up to the highest value. This diagram can also be turned vertically sometimes, but horizontal is pretty common as well, right? So for example, let me draw box plots for both data sets in above. Make these a little bit smaller. Okay. So we have these data sets. They range from 20 to 100. So let's say I put a scale. So remember, a good chart has a nice title. Okay. So what you can do here is you can set up a scale. So this is say 0 to 100. We know that all the data happens from 20 onwards. Okay. Now what we're going to do here is we're going to look at the quartiles. So for set 1, the first quartile is at 45. The second quartile is at 68. The third is at 75. So I'm going to go over here. 45. 68. 75. Right? And we know the lowest value was 20 and the highest value was 100. So for set 1, let's draw that in, say, blue. So it's going to go from 45 all the way to 75. And that's where the box is. The median occurs at 68. There's a whisker extending to the highest value, which is 100. There's a whisker extending to the lowest value, which is 20. That's the box plot. That's how you do it. So once you can find the quartiles, which is just a matter of finding medians, you can get to the box plot relatively easy. So yeah, so this is set 1 is the blue line. Let's do set 2. It's going to be the red line. So for set 2, what were the important numbers? Oh, Q1 was 90, 95, and 98. So they're all way up here. So look at 90, 95, 98. Okay. So now that's here, 90 up to 98 and 95. 5 is over there. Have a little whisker extend because it's not far to get to 100. And then you have a long whisker extending all the way down here. Right? So you can clearly see here, there is definitely less variation in set 2. Most of the data, in fact, half the data is in the 90s, right? 50% of the data is in the 90s. You have 25% of the data extends all the way from the 90s to the 20s, which is not a lot of the data. And then another 25 extends out to 100. But clearly you can see here with these two graphs, even though they had the same range, it's clear that the grades for set 2 were higher in terms of the median, and more the students were closer together in terms of grades, right? Most of the students here got in the 90s, and you can see that by a very small box, right? So that's a box plot. You can plot them on the same graph, and you can actually compare them. So that's nice. Another very common way of comparing spread or variation is called the standard deviation. And this comes in two main flavors. In statistics, there's always a concern with how you can get your data. Sometimes it's not possible to get all the data you would need. So for example, sometimes you're looking at polls. So for like, say, election results or something like that. Oh, we believe in this state, this percentage of people will vote Democrat, that percentage will vote Republican. The thing is, you can't interview everyone, right? Like you can't actually go through the United States. I mean, I guess you probably could, but it would take a lot of manpower, a lot of time, a lot of money. You wouldn't want to, even if you could, right? To interview all 350 million people. What you can sometimes do, though, is take what you call a representative sample. So you don't pick everyone. You pick a few people that you think would represent everyone, right? Because they're how they were selected was random. How they were selected would go through every demographic, every kind of different opinions. And once you can come up with a smaller group of people that you can think represents the entire population, this is called a sample or a random sample. So there are times when you can do calculations for the sample, and the point of doing that is to approximate what the actual values are for the entire population. And there are times when you can do samples, take measurements for the entire population. So this gives us two kind of varieties that we can do here. So there's the sample standard deviation, and there's the population standard deviation, which, by the way, this idea of population and sample, it's more general than standard deviation. It also occurs for mean, for example. So you can look at the mean of the sample versus the mean of the population, and that's also given different notations. So if we have values, x1, x2, x3, all the way up to xn, and we think of that as a sample of n data points, then the mean notation is usually x bar, x with a little bar over it. If we think of those n values as the entire population, like we actually measured everybody, then you'd use the Greek letter mu, which you have here, right? So you can have the notation x bar, which is right here, or you can have the notation mu, and that goes with population. So sample mean is x bar, population mean is mu. Okay, so that's just the notation that we always use. Okay, now once you know all that, okay, there's a sample standard deviation, which is, say, the S, and then there's a population standard deviation, which is the Greek letter sigma, lowercase sigma. We want to be able to measure this sort of variation, which it has a very interesting formula. What the standard deviation attempts to do is to find how much data points are spread out away from the mean on average, right? How far away from the mean is the average data point? And This doesn't exactly measure that. It's kind of an approximation, but I don't want to go through the derivation of this formula because you don't have to know. But you can just know that it's measured by this formula. Okay, so if you have, and this might remind you of like a distance formula, right? Where you have each coordinate measuring its distance from some central coordinate, which is the mean coordinate. But let's not get into that. And we're dividing by n minus 1, not n because it's a sample. We found that dividing by n minus 1 for reasons that are way above our pay grade makes it actually more accurate for the population as an approximation to the population standard deviation. But this is going to be the formula. You take each value, you subtract the mean of the sample, and you square it, you add them all up, and then you can divide that by n minus 1 and take the square root. This gives you what's called a standard deviation. To write this down in a shorthand formula, which I mentioned that I will give you, that's probably the formula I would give you in the exam. I would say it's the summation. I goes from 1 up to n of xi minus x bar squared all over n minus 1, and then you take the square root of that. And that would be the standard deviation, right? So a very big formula. Depending on your calculator, it might be very annoying to actually plug this in all at once. But I'll show you a couple ways to actually do that. Sometimes it's nice to do it in a table format to get to this answer. But that's the formula for population standard deviation. And this is the one I'll be asking you about most of the time. And again, remember this entire section is in the bonus section, so you technically, you can get away without this. But I think just knowing that you can just plug in these numbers into this formula and just get an answer, I think it's worth actually taking a few moments to practice using this. The population standard deviation, if I assume that the x1 through xn account for everyone, then it's a very similar formula, except now it reminds you of the actual average where you divide by n and then you take the square root. There's another measurement that's very connected to standard deviation. It's called the variance, right? So we have the variance as well, which is simply just the square of the standard deviation. So the sample variance is just s squared. The population variance is sigma squared. And these are the formulas. Okay, so let's actually just do some examples so we can actually see how to compute this. Okay, so we're going back to set 1 of the grades that we saw earlier, and I want us to compute the standard deviation and the variance of this, this data set. Okay, so the first thing we need to do is we need to find the mean, right? So, and we're again thinking of a sample here, so that tells you what formula we should use. But you're always going to find the sample. I'm never going to ask you to do something for a population. Always just assume it's a sample because there will be a very small number of values. So now what you would do here is first find the mean. That's going to be the sum of all these values divided by the number of values. Okay, now I computed this last time I recorded, so let's see what that is. I think it was 66 or 60. Okay, I got, this is 62.667. Well, that's not what we want the standard deviation, but we're going to need this, right? So now, to go to the standard deviation, what you're going to do is you're going to take each value, subtract that, square it, add them together, divide by n minus 1, then take the square root, right? Which seems like a lot, but you can, if you have a nice calculator where you can kind of see how you're typing things out and you know how to use this properly with parentheses, you can do it. So this means that the standard deviation is going to be, you're going to take each value. So 20, 45, you're going to subtract the mean, square it, add it together. So you're going to take 20 minus the mean, you're going to square it. Then you're going to take 45 minus the mean, going to square it. You're going to take 66 minus the mean, going to square it. You're going to take 70 minus the mean. You're going to square it. You're going to take 75 minus the mean and square it. And finally, you're going to take 100 minus the mean. And you're going to square it, right? So that's your numerator, right? So make sure you don't make a mistake plugging that into your calculator. Then what you're going to do is you're going to divide all that by n minus 1. So it's 6 minus 1. And then what you're going to do is you're going to take the square root of all of that. And in this case, you should end up with, I think the answer is 27.362. So that's your standard deviation. Now your variance, well, that's equal to s squared, right? So that's going to be roughly 27.362 squared, which is 748.667. And that's the standard deviation and the variance. Okay, so it's a very long formula, even for just 6 values, but it's straightforward in terms of you just plugging things in. You find the mean, they take each value minus the mean, square it, add it together, divide by n minus 1, take the square root. It might be easier to do this in a table, so let me show you that. Maybe easier to set this up in a table. Okay, so the table, you would normally just go through and compute the individual parts that you need. So you'd have the xi's, then you'd have the xi minus the x bar. Then you have the xi minus x bar, and you're going to square it. Okay, and now you can actually go through and do it this way. So we have the xi are just the data points. So the xi is going to be like, okay, you're going to have the 20, you're going to have the 45, you're going to have the 66, you're going to have the 70, you know, the 75, you're going to have the 100. Okay. And what you're going to do here is you're going to find the total of this part over here. So you can go through and you can just compute the differences, right? So here you're going to take, we know x bar equals 66.667. So we're going to actually do that and subtract, take 20 minus that, take 45 minus that, take 66 minus that, take 70 minus that, take 75 minus that, take 100 minus that, right? So here you would end up with minus 42.667. Here you'd end up with minus 17.667. Here you would end up with 3.333. Here you would end up with 7.333. Here you would end up with 12.333. And here you'd end up with 37.333. Right? So you just do that. Then you're going to square each of these terms. So if we take 42.667, you square it. You can ignore the negative because you're squaring. You would get 1820.444. Square the 17.67, you would get 312.111. Square the 3.3, you get 11.111. Square the 7.33, you get 53.778. Square the 12.33, you would get 152.111. Square the 37.3, you would get 1393.778. Right? You can just do this in your calculator line by line. Then what you're going to do is you're going to add up all these numbers. So you're going to take 1820.444 plus 312.111 plus blah, blah, blah. You add those guys all up. You'll get about 3743.333. Right? So that's the thing in the numerator under the square root. Get some space here. And so from here, what you can do is you can find these variance s squared. That's going to just be this guy, 3743.333 divided by n minus 1. Okay, and that is going to be 748.667, which we got last time. And so that's the variance. And then your S is just going to be, well, the square root of that, 3743.333 all over 6 minus 1. And that would be the 27.362, which is the standard deviation. So that's how you can do it in your table if your calculator is kind of weird and you can't really plug it all in. And this will be very annoying for you to do. You can do it in a table if you want. Just compute one line at a time, then add them together. There's one other situation that I want you guys to know about, and that is the grouped data situation. Now we've seen grouped data before. So this is just when we have a bunch of data points and we just put them in groups, like in bins. So we had those grades where, and I think I'm going to reuse that same example. We had a list of 20 grades before, remember, and we put them in bins between 50 and 60, 60 and 70, 70 and 80, 80 and 90, 90 and 100. Remember that? And so, yeah, we did that. So now the question is, if you have data group like this, how do you go about approximating the mean and the standard deviation and the median, right? So if you're the thing is, we no longer have all the specific numbers. We just know the bins or the groups that we're putting the data in, and we know how many points are in those groups, but we don't actually know the actual data, right? So the question is, how do you go about computing the mean, the median, and some like standard deviation from group data. And the idea is the following. For the mean and the standard deviation, what you do is you pretend all the data points in a group take on the middle value in that group, right? Which is the median of that bin. And then it just means for those xi, you're just copying that number down, the median value. So it turns out that you'll have the frequency, right? How many times that guy appears is going to be how many of those squares that you're adding up in these standard deviation. It's also going to be the number of times you're multiplying, you're adding that number in the mean, right? So you're going to add a certain number a certain amount of times, and that number of times is going to be the frequency in the bin. I'm going to show an example, so you don't worry if you're confused yet. For the median, it's a little bit different. What we're going to do is we're going to assume that all the values in the bin are evenly spaced, and then we're just going to, again, count how many values that we need to get to median, and we're just going to take the middle value, right? You're going to divide the number of data points that you have by 2. Whatever answer you get, you take that value. Yeah, and so let's actually see how that would work, right? So now if we have the, suppose we have k bins, so we have n data points, but we have k bins, right? So we put them in k groups, okay? So, and I'm calling the number of the group by the letter I. So you can have I equals 1 for the first group, I equals 2 for the second group, I equals 3 for the third group, all the way up to I equals k. And we have frequencies for each group, so which is f sub I. So f1 is going to be the frequency in the first group, f2 is the frequency in the second group, f3 is in the group, etc. Right? And we can then use these formulas. So for the mean, here's how we're going to do it. Again, remember, we're going to pretend that all values take on the value of the median in the group. So the mean would be given by, well, you're going to take the median value in the first group multiplied by the frequency in the first group, plus the median value in the second group multiplied by the frequency in the second group, going all the way down to the median in the kth group times the frequency in the kth group, and you're going to divide that by n, the number of original data points that you had. You can write this down as, well, it's going to be the sum of x sub I, f sub I, where your I goes from 1 up to k, where k is the number of groups. Then you're going to divide all that by n, right? So that's the shorthand formula. Standard deviation is going to be very similar because we're repeating values, so we're going to be adding up the frequencies. So the standard deviation, S, is going to be equal to, well, you're going to have x1 minus the mean and square it, but your x1 is going to repeat for all the values in the first bin. So you're going to multiply that by f1 because that's how many were there. Then you're going to take x2 minus this guy, where x2 again is the median of the second bin, multiply by the frequency, plus dot dot dot, xk minus x bar squared times fk, all over n minus 1, and then you take the square root. Okay. You can write this in shorthand by the following. From I goes from 1 up to k. K is the number of bins. You have xi minus x bar squared times fi, all over n minus 1, and you take the square root. So that's going to be your formula there. The median is a little bit tricky. Well, it's not tricky. I mean, it's just how it's done You pretend the values are evenly spaced. So you don't pretend they all take on the value of the median in the middle. Pretend they're evenly spaced throughout the bins. And then you can count how many numbers you need. So usually this is going to be find how many values are needed to get to the median. Determine which bin this value would be in. You're then going to pretend values are evenly spaced. And count up to the value you need. Need some more space here. This leads to, so now in terms of a formula, it's going to be the median is going to be the left endpoint of the required bin plus you're going to take the number of steps needed to hit the median, number of steps needed to hit median, times the bin spacing. Spacing between each number. So that tells you the size of the steps you're making, and then you're going to count the number of steps you're making, and that will tell you how many numbers you have to get into the bin, and then you add on the left side, and that gives you all the numbers up to that point. Spacing between the values in the bin. Okay. Now again, these might look confusing at first, but let's actually do an example so you can see how this would work. So this is an old example. Okay, see how much time. Actually, I forgot to look at what time I started. I think we're still within a lecture, but we'll see, I guess, when I'm done. So we've seen this example before. This was the list of 20 grades, and we actually grouped them like this. We use that to draw a histogram and all that stuff. Okay, cool. So we're not going to do that now. What we're going to do now is we're going to find the mean, the median, and the standard deviation of grouped data. So right now I'm pretending I don't know what these specific values are. All I know is this. I know there are 3 values between 50 and 60. There are 6 values between 60 and 70. There are 5 values between 70 and 80. There are 4 values between 80 and 90. There are 2 values between 90 and 100. I don't know specifically what these values are, but for some reason I need to estimate the mean, the middle, blah, blah, blah. Okay, so what we're going to do is here, the xi are, well, what are they? Remember, we pretend we want the values to be the middle value in each bin. So for the 50 to 60, that would be 55. 60 to 70, that's 65, then 75, then 85, then 95. So this is 55, 65, 75, 85, 95, right? The middle numbers, right? Now, what I'm going to do is I'm going to pretend, for the sake of the mean and the standard deviation, that all values in the 50 to 60 bin take on the value 55. All values in the 60 to 70 bin take on the value 65, right? So there are 3 values of 55, 6 values of 65, 5 values of 75, 4 values of 85, and 2 values of 95, right? So this would mean that the mean would be, well, technically it's approximately, because I'm not even actually calculating the actual mean. It's going to be 55, but there are 3 of them, right? And then it's going to be 65, but there are 6 of those. And it's going to be 75, but there are 5 of those. It's going to be 85, but there are 4 of those. And it's going to be 95, and we're assuming there are 2 of those. Over 20 when I get to the total, which is, I'm told here, 20, right? So there are 355s, 665s, 575s, 485s, 295s, right? So I just take the frequency times the middle number in each bin. Add them all together, divide by the number of numbers there are, and that gives me, here, this actually comes out to a nice round number, 73. By the way, in case you're interested, FYI, the actual mean, like if I were to actually calculate based on the specific numbers, it's actually 71.95. So it's actually pretty close, right? It actually saves me a lot of work to do this than to actually compute the actual mean. And I get a pretty reasonable answer, even with just 20 data points. With more data points, your answer actually gets better. So yeah, that's cool. Now, what about the standard deviation? Right. So now S is going to be, again, we're going to take each data, so 55 minus the mean, square it. But remember, there are 3 numbers like this, because that was the frequency in the 50 to 60 bin, 3. There are 6 numbers that I'm believing take on the value 65, 5 that take on 75, 4 that take on 85, 2 that take on 95. So that's going to happen 3 times. I'm going to add that square. Then there are going to be 6 times when I add this square. There are going to be 5 times where I add the square of 75 minus 73. There are going to be 4 times where I add the square of 85 minus 73. And there are going to be 2 times where I add the square of 95 minus 73. All over 20 minus 1, then take the square root. Right? Now, this is a lot shorter than if I were to do the standard deviation for each specific value, all 20 values. I would need like 20 of these squares extending forever. But here I can just clump it into 5 groups. Right? So that's nice. And I can compute that here. This will give you 12.397. FYI. The actual standard deviation, if I were to actually do it for the 20 values, specific values, it's again pretty close, 12.284. Again, a lot less work and we get a pretty okay answer, right? For some context that can be completely reasonable. Standard deviation is around 12, right? In fact, with rounding, and we can see it's 12.3, 12.4-ish. That's pretty close for all the work it saved us. Let's look at the median. So the variance, we didn't do that. Variance. Actually, didn't do that last time. We do it now. 12.9, 12.397 squared. That would be 153.686. We have that. Let's look at the median. I have 20 numbers, so I'm going to first find the median position. Divided by 2, so it's roughly the 10th position. Yes, I know it's going to be the average of the 10th and the 11th position, but it's an approximation anyway, so we don't have to be totally crazy about it. So yeah, roughly the 10th position is what we want. So you know, this leads to the 70 to 80 bin. How do I know? Well, there were 3 in the first bin, 6 in the second. That accounts for 9. So I need 10. So I need 1 more in this bin. Okay, and so the median is going to end up in the 70 to 80 bin. Okay. Now I'm going to find the spacing of all the values. So the bin length obviously is 80 minus 70, which is 10. So this means the bin spacing is 10 divided by the frequency in that bin, which is 5. So I have 5 values evenly split over a length of 10, which means that the spacing between each is around 2. There are 2 units of spacing between them, right? So that's your bin spacing. So now the steps needed is 1, right? We have 9 numbers accounted for already. Need 1 more to get to 10. So now you can use that formula. So we can say the median equals the left point left endpoint plus number of steps times bin spacing. Left endpoint was 70. We're in the 70 to 80 bin. Plus the number of steps is 1, and the bin spacing is 2. So this is 72. And that is our approximation for the median, 72. FYI, actual median 71. So we're approximating this without even knowing what the specific values are. And we're getting actually numbers close to the actual values, which is the power of these formulas. You don't have to know why the formulas are the way they are, but hopefully that kind of convinces you that they can work reasonably well. At this point, I would say as an additional example for more practice, you can go back to the mock exam for test 2. In the bonus problem, I asked you to compute the mean and the median. I didn't ask you to compute standard deviation, but you can go back, you can compute that, the mean and the median, and I gave you the answers for the mean and the median. However, I didn't give you the answers for the standard deviation. So the standard deviation was that you should get using these formulas is 15.852. And the variance that you should get using these formulas is 251.2821. Okay. Yeah, and we will stop there. So that is variation. So you should know about range, which is highest value minus smallest value. You should know about quartiles. Q1 is the median of all values below the median. Q2 is the median of the entire data set. Q3 is the median of all values above the median. Using those, you can find the interquartile range, as well as you can draw a box plot. Standard deviation is given by this formula. And for grouped data, which you can do in a table if you want, and for grouped data, these are the formulas you can use. And for the median, it's like a method, not necessarily a formula, and you can do that. So you can go over the examples, make sure you can do those, and that's that, I think. So I guess we'll stop there. So I'll see you guys in the review, and as well as I told you when the final exam dates were. So if you have any questions prior to that, you can let me know. But for now, we are going to get out of here. That is it. Thank you for your time and attention, and I will see you guys in the next one. Ciao.